All right, so can you hear me, everyone?
Yes.
Yep.
Okay, perfect. It's 8:18 by my clock. I will wait for a minute and a half. Does anybody have any questions from class 1, from the first lecture? Anyone? For some reason, this is not showing me the chat. How do I see the chats? Let's see. So, David, Alex, you guys are going to have to monitor the chat because I'm unable to see the chat on my screen for some reason.
Okay.
Professor, I just wanted to mention that I just joined in to see how lecture works. Yeah, today I think Charles is also the shadow.
So whoever,
Yeah. Okay.
so whoever is shadowing it, just make sure that you're tracking the chat, right? Yeah. All right, guys. No questions. Okay. If that is the case, then I'm going to assume that everything was nice and clear. So without further ado, actually it's 8:19. I'll start exactly at 8:20. Another 30 seconds. Okay, it's 8:20. Let's begin. Right. So in the last class, we saw a bit of what neural networks are. So we're going to continue with the same theme. In this class, we are going to see what a neural network can represent. So here's a quick recap. We saw in the last class that in many AI tasks, neural networks have taken over. These were tasks that were previously considered to be solely in the domain of human expertise, like speech recognition or machine translation, even driving cars, imagining things. And now artificial neural networks have actually taken over many of these jobs, and they're often even better than human beings are. So what are these amazing neural networks? In each case, the neural network is a function that takes in some input and produces some output. So it may take in an input voice signal and produce a transcription, or it may take in an image and produce a text caption, a current game state, and a prediction for the next game state. So this is a function that takes in some input and produces some output. But what's in these functions? If a human were to perform these tasks, those functions would be computed by the human brain. And so neural networks mimic the network structure of the human brain. Now, we saw in the last class that the brain in turn is a giant network of neurons where the neurons themselves are these little units that fire when the combined input exceeds a threshold. And so artificial neural networks too are networks of computational models of the neuron. This computational model of the neuron is what we will call a perceptron. Now, we saw that a perceptron is a unit of this kind, which receives many inputs. It has a weight associated with each input. If the weighted sum of all of the inputs exceeds a threshold, the neuron fires. I've alternately called the perceptron a neuron because we're speaking of neural networks and they model neurons. So I may use the word neuron or perceptron interchangeably. So anyway, going back to our discussion, when the weighted sum of the inputs exceeds the threshold, the neuron fires. If the weighted sum does not exceed the threshold, then it doesn't. So in electrical engineering terms, this perceptron is a threshold gate. It implements threshold logic. And again, remember this term threshold logic. You're going to see it a few times during this lecture, and it is on the slides. And it will also come up in the quiz. So here's a different way of visualizing the perceptron. We first compute. If you have several inputs, the perceptron has several inputs. You first compute an affine function of the input. So does anyone know what an affine function is? what is an affine function, guys? Linear plus constant term, right? The difference here, anyone else? Is that just one person replying? If you know the distinction between an affine function and a linear function, raise your hands. It's not many, right? So I'm not speaking of an affine combination Boolean. An affine combination is a weighted sum where the weights sum to 1. I'm speaking of an affine function. So here's one way of thinking about it. Let me sort of demolish my my screen a little bit, or actually, if I can, maybe I have my whiteboard. That is my whiteboard. I thought it. Oh, yeah. So think of a function. Say this is x, x1, x2, right? And if I have a function of this kind, and this can be in many dimensions, if I have a function of this kind, summation xi wi equals 0, this, what is this an equation of? Anyone? What is this an equation of?
A line through the origin.
A hyperplane through the origin. In this case, it's going to be a line through the origin, right? So this is going to be something of this kind, which goes through the origin. Now, on the other hand, if you have something that is also a hyperplane or a line but does not go through the origin, what is the equation going to be?
Addition of a constant term.
That's just going to be summation wi xi plus b, right? So this is an affine function. This equation for this line is f of x equals 0. F of x is this particular form. This is an affine function, and this is a linear function. So I assume that everybody sees the difference between the two. I'm having trouble finding. Come on. My screen is too small. Anyway, so over here, this affine function is a weighted sum of the inputs plus a bias. And the bias over here is minus t, which is, when you set the bias to be minus t, you get exactly the same perceptron as the one over here. And so you can think of the perceptron as this model where you first compute an affine function of the inputs, and then you put the affine function through this affine value, z, through this function, which outputs a 1 if the affine value is greater than or equal to 0 if it's positive, and 0 otherwise. And this entire operation is your perceptron. Now, once you think of it this way, then you can see that you can actually replace this function over here with other functions. You can have a soft version of this perceptron, which would use a squashing function instead of a threshold function. So this is a sigmoid rather than a threshold. And the function that we put the affine value through is what we will call an activation. So first you compute an affine value, you put it through a threshold activation, and you get the output of the perceptron. But the entire perceptron, again, is simply outputting a 1 if the weighted sum is greater than the threshold and 0 otherwise. Instead of having a threshold okay, here's a little poll. Okay. All right, guys. So The first one is a linear combination of x and y. The second one is not a linear combination. You see this constant for this additional constant 4. So this makes it an affine combination of x and y. The third one is actually now a linear combination, a linear function is actually a special, a linear combination is actually a special function of an affine function. So the third one is actually an affine function, as is the fourth. Anyway, going back to our problem, right? Once we state it as computing an affine function of the inputs and passing it through an activation, then you can use other kinds of activations like the squashing function here, which is a sigmoid, and the difference between a sigmoid and the threshold is whereas the threshold just goes up suddenly, a sigmoid would be somewhat smoother and do something like this, right? It's still the same thing. It's a smoother version of it's a continuous version of the threshold. And as you can see, as you'll see later, there's a lot of benefit to replacing this threshold by this continuous function. You can also have other kinds of activation functions like the tanh, which is simply a scaled and shifted sigmoid. The activation function doesn't even have to be a squashing function, which restricts the range of the output. For example, you can have an activation function of this kind, which is this red line is the ReLU, which simply truncates negative values, but passes positive values through unchanged, or its smooth differentiable version, which is this blue line, which we'll call the soft plus. For now, we're going to continue assuming this threshold activation because it helps us develop intuitions much better. Now, a multi-layer perceptron or an MLP is a network of such perceptrons where the perceptrons receive inputs from other perceptrons, and these perceptrons are arranged in layers. Now, we will see a formal definition of what a layer is in a few minutes. Now, when these networks, but before that, there's the topic that we are all interested in is deep neural networks. So what do we mean by saying a network is deep? Does anybody know? Does anyone know what it means for a network to be deep?
Multiple hidden layers.
Multiple hidden layers. Exactly how many?
2 hidden layers.
2 hidden layers. Yeah, but there's a more formal definition for depth. Now, when these networks have many layers, they're called deep. But again, when you're speaking of deep networks, you're thinking of networks as graphs. In any directed graphs with sources and sinks, the depth of the graph is simply the length of the longest path from the source to the sink. So in this graph, for example, you have a path from source to sink, which is one hop long, but you also have a path which is 2 edges long. So this graph has a depth of 2, not 1. This graph has 3 different paths from the source to the sink. You have this one path with just 1 edge, one with 2 edges, and one with 3 edges. But the depth of this graph is 3. That's the length of the longest path from the source to the sink. And so when we speak of deep neural networks, we apply the same principle in defining the depth of a network. Now, the computation in a neural network is generally directed from the input to the output. And the depth of the network is the length of the longest path. That is the maximum number of perceptrons or neurons from the input to the output. So in this case, the depth of the network over here is 1, 2, 3. Now, when the depth of the network is greater than 2, then the network is called deep. Now, can anybody tell me what is the depth of this network over here, assuming that all of these, this is just one collection of neurons at the same at the same level. So what would the depth of this network be? Anyone? This one's easy, guys. What is the depth here?
If you can't see chat, there's a lot of people saying 2.
2, okay. What about this one over here?
People are saying 4.
1, 2, 3, 4, correct, right? So also, we speak of layers. What do we mean by a layer? Does anybody know what it means for, or what the term layer means in this context?
All the neurons in the same layer are at equal depth.
At equal depth with respect to the input, right? So a layer is the set of all neurons that have the same depth from the input. So in this figure over here, all the green neurons are at depth 2 with respect to the input. So these form the second layer. All the red neurons, observe that there is a path of length 1 from the input to these green neurons. That doesn't matter because the longest path to the green neuron is 2. So these neurons are at depth 2, so these neurons form the second layer. These red neurons are all at depth 1, so they form the first layer. These 2 yellow neurons, but not the green neuron. These 2 yellow neurons are all at depth 3 with respect to the input. So the third layer in this network is the set of these 2 yellow neurons, and these 2 blue neurons form the fourth layer. So you get the idea of what a layer is. Now, so moving on, here's how we've defined our multi-layer perceptron. It's a network of perceptrons, which we'll also call neurons sometimes. The nodes in the network are these neurons or perceptrons. The edges represent the connections between these perceptrons, and each edge carries a weight. The network performs computations. It takes in an input and produces an output. The inputs can be real or Boolean. The outputs too can be real or Boolean, or real or Boolean. And now we have so far seen networks with a single output in my illustrations, but the network can in fact have multiple outputs or a vector of outputs. So overall, the network in fact represents a function that embodies an input-output relationship between its inputs and its outputs. Now the question is, what kinds of input-output relationships can the network model? What kinds of functions can it compute? Now, we've already seen that MLPs can compose Boolean functions, which operate on Boolean inputs and produce Boolean outputs. We've also seen that, like this network over here, we've also seen that MLPs can compute real valued functions. They can take in real valued inputs and produce real valued outputs. For example, we saw in the last class how to construct a network that approximately computes the function shown by this blue curve. Now, so we can compose these functions which construct these networks which compute Boolean functions or real functions. But what are the limitations? Can we always construct a network to compute any function, or are there limitations on what kinds of functions we can model with a network? And if so, what are they? So that is the topic of today's lecture. We will see that multi-layer perceptrons are universal Boolean functions. What I mean by saying that a multi-layer perceptron is a universal Boolean function is that if you give me any Boolean function at all, any Boolean function, I can construct an MLP that computes it. In this context, we will discuss why it's necessary for the network to be deep. We will also see that MLPs are universal classifiers, meaning you give me any arbitrary decision boundary, and I can construct an MLP that captures it arbitrarily accurately. And again, we will discuss the need for depth in this context. And finally, we will see that MLPs are universal approximators. Give me any input-output relationship at all between reals and reals, complex and complex, it doesn't matter. And I can construct an MLP that approximates that input-output relationship to arbitrary precision. And in this context, again, we will discuss the issue of the optimal depth and width of a network. The slide deck also includes some discussion of radial basis function networks, which is somewhat off tangent. So I won't discuss it in class, but it's something that is interesting for you to know. So we will have a question about that topic, RBF networks, in the quiz. But first, let's discuss MLPs as universal Boolean functions. We know that MLPs can model Boolean functions, but how well do they do it? We know that individual perceptrons can model Boolean gates. We saw these figures in the last class. They show how a perceptron can model the AND, NOT, or gates. To remind you, in this figure, the numbers on top of the edges represent weights. The numbers in the circles represent thresholds. This perceptron and each perceptron outputs a 1 if the total weighted sum of inputs matches the threshold. So this perceptron to the top left, this is going to only fire if both X and Y are 1, because only then the total input is going to be 2. So this is an AND gate, X and Y. This perceptron outputs a 1 when X is 0 and a 0 when X is 1. So this is not X. This one only outputs a 1 when both X and Y are 1, because otherwise the total sum coming in is not going to match the threshold. So this is X and Y. I think I have the symbols kind of mixed up. But then a perceptron can do a lot more than that. The perceptron is in fact a universal AND gate. So consider this one over here. This perceptron will fire only if inputs X1 through XL are all 1, and if inputs XL plus 1 through XN are all 0. And under no other condition will this perceptron fire. Now, to see why this is so, consider the case when all of these guys are 1 and all of these guys are 0. So if all of these first L guys are 1 and all the remaining inputs are 0, what is the total weighted input coming in over here? Anyone? L, it's going to be L, right? And now, if I flip any one of these bits, so if I convert any one of these guys from 0 to a 1, what will happen to the sum that comes in?
L minus 1.
Same thing, right? And so also if I flip any of these guys, it's going to become L minus 1. So this one only fires if these guys are 1 and these guys are 0 under a very, very specific condition. Similarly, here's a perceptron that's a universal OR gate. It will fire if any of the first L inputs is 1 or if any of the subsequent inputs is 0. Now to see why this is having a threshold of L minus N plus 1 with negative weights for these guys and positive weights for these ones satisfies this Boolean function, let's first consider the only condition under which it will not fire. What is the only condition under which it will not fire? Anyone?
All inputs are 0.
All inputs are 0? No. So remember, I want this to fire if any of these guys are 1 or if any of these guys are 0. If all inputs are 0, it will fire. What's the condition under which it will not fire?
All the 1 to L1s are 0, and after that they are all 1.
So if all of these are 0 and all of these are 1, that is the only condition under which it will not fire. Under that condition, what is the total weighted sum coming in? It's going to be, there are N minus L terms over here. They all have a weight of -1. So it's going to be L minus N, right? And if I flip any one, it's going to become L minus N plus 1. And so basically, this one is going to fire if any of these guys are 1 or any of these guys are 0. This is a universal OR gate. This one over here will fire if at least K of the inputs are 1. And you can see why. All of the inputs have weight 1. And if any K of them are 1, then it's going to match the threshold and it's going to fire. So this is a generalized version of a majority gate, a gate that will fire if a majority gate is a gate that will fire if the majority of the inputs is 1. This is a generalization of it. And so you can see that the perceptron is much more than a simple Boolean unit. It's a very versatile unit and can model all kinds of crazy Boolean functions all by itself, which is why Rosenblatt got fooled into thinking it could do any Boolean function at all. And yet, the perceptron cannot model the simple XOR function. There's no combination of weights and threshold for which it's going to compute an XOR. To compute an XOR, you're going to have to network multiple of these perceptrons. You need a multi-layer perceptron. So this, for example, is a network that computes XOR. It's a network of 3 perceptrons with one hidden layer whose outputs you don't directly see, and an output perceptron. The structure is kind of obvious. This guy computes X or Y. This computes not X or not Y. You AND the two and you get an X or Y. In fact, you can have a smaller structure to compute an XOR. I got this from Gerald Friedland at Berkeley. This one only uses 2 perceptrons and 5 weights. And the weights now are not all 1, but this will compute X or Y. And you can work it out and figure out how it is. In fact, you can show that you need a minimum of 5 edges in order to compute the XOR of 2 inputs and 2 neurons. Now, the upshot of this is that since we can compute all basic Boolean gates using perceptrons, we can, in fact, construct an MLP for any Boolean function, like this weird one over here, which computes a function of 4 inputs. So MLPs are, in fact, universal Boolean functions. Regardless of the Boolean function you give me, I can always construct an MLP that computes it. So MLPs are universal Boolean functions. They can be constructed to compute any Boolean function over any number of inputs and any number of outputs. But how complex will the network get? Now, in the example here on the left, we see that in order to compose this function on the top, we used 7 neurons and they were arranged in 3 layers. So the MLP that computes this function over here has 2 hidden layers. If I had a more complex function of a larger number of inputs, then how many layers would my MLP need to have to compute it? Can anybody give me a guess as to how the depth of the network relates to the complexity of the Boolean function it computes? Anyone want to take a guess?
It could be the number of gates in the reduced form.
The number of, so I'm speaking of the depth.
Okay. I'm not sure then.
Okay.
Power of 2.
2. You're right, right? Consider this. Who said that? Who said 2? Whoever did, you were right. So consider this. Any Boolean function is basically just a truth table. It takes a number of Boolean inputs and outputs a Boolean variable and outputs a Boolean value. So you can write out the entire function in this tabular format, where you write out every combination of inputs that produces a 1. So you can basically list all combinations and the corresponding output, but you don't need to list the combinations for which the output is 0 because that's implicit. So this truth table represents a Boolean function. And once you write it in this manner, so pretty much any Boolean function can be written as a table, because inputs are Boolean. You can list out all combinations of inputs and the corresponding output, and you only have to retain the combinations for which the output is 1, because for the rest, the output is implicitly 0. Then once you write it in this manner, you can write out the Boolean function as a DNF formula, a formula in disjunctive normal form. The DNF formula has clauses. Each clause represents one of the combinations of the input for which the output is 1. So in each clause, it's an AND of several terms. It's an AND of either of several variables, where when I write not variable, it means that that variable must take the value 0. So for example, this one over here, not x1, not x2, x3, x4, not x5, says that x1 must be 0, x2 must be 0, x3 must be 1, x4 must be 1, and x5 must be 0. So when this combination happens, the function takes the value 1. The plus represents the OR. So this clause over here is not x1, x2, not x3, x4, x5. This clause over here is not x1, x2, x3, not x4, not x5. And so I can write out one clause for every combination for which the input is, for which the output is 1. I can sum them up, which is the summing is an OR, and this formula is the Boolean function that I'm trying to compute. I can write this DNF formula for any Boolean function at all because I can represent any Boolean function as a truth table. But once I do this, I can compose an MLP for this formula. I can have one perceptron for each one of these clauses. And then finally, I can have one final perceptron, which simply ORs the outputs of these individual clauses. And now you have an MLP that exactly computes this Boolean formula. And you can model any Boolean function in this manner because any Boolean function can be expressed as a truth table. Note that this network has only one hidden layer where each neuron computes one of the clauses in the DNF formula. This means that any Boolean function can be modeled by an MLP with only one hidden layer. So a one hidden layer MLP is a universal Boolean function. But then how large does this MLP get? How many neurons will be required in this one hidden layer to represent an arbitrary function of n variables? In other words, how large do these DNF formulae get? To answer this question, let's look at the truth table in a different way, in the form of a Carnot map. How many of you are familiar with a Carnot map? How many of you have heard of this Carnot maps? Quite a few, right? So not everybody ISM, but quite a few. A Carnot map is a topological way of representing bit patterns such that patterns that differ by only one bit are always arranged next to one another. For example, this is a Carnot map over four variables, W, X, Y, and Z. The 4 rows represent the 4 combinations of W and X. So this is 0, 0, 0, 1, 1, 1, 1, 0. Similarly, the 4 columns represent the 4 combinations of Y and Z. So all in all, these 16 grid cells represent all 16 combinations of these 4 variables, except that any grid cell now differs from its neighbor by only 1 bit. So consider these two guys. This is 0, 0, 0, 0. This is 0, 0, 0, 0, 0, 1. Or consider these two guys. So this is 1, 1, 1, 1. And this guy is 1, 1, 1, 0. So any two cells only differ by 1 bit. Also, the rightmost edge is connected to the leftmost edge because each of these cells differs by only 1 bit from the cell over here. And similarly, the topmost row connects to the bottommost row because the bit patterns here differ by only 1 bit from the patterns in these rows. And so, although I've represented this as a square, this square grid is in fact a torus, where this edge connects to this edge and this edge connects to this edge. It's like a donut. And it represents a topologically correct representation of all patterns of these 4 variables. Now, when we use this to represent a truth table, then the 16 boxes represent the 16 possible combinations of the 4 input variables, and the highlighted boxes represent the input combinations for which the output is 1. And so, for this function, there are 7 input combinations that produce an output 1. A naive DNF formula would therefore have 7 clauses. But now you can begin grouping neighboring boxes to reduce the size of the DNF formula. For example, if you look at these 4 boxes over here, the 4 boxes in this first column all produce the output 1. It means that if y and z take the value 0 and 0, it doesn't matter what values w and x take, the output is always 1. So I can group this 4 boxes into a simple DNF formula, which is not y, not z. Similarly, these two guys, they too produce the output 1, which means that if wx is 0, 1 and y is 0, then it doesn't matter what the value of z is, the output is 1. So I can have one DNF clause for this group, which is not w, x, not y. And I can similarly group these two guys, and it's going to give you not x, y, not z. And by this grouping, in fact, I can group the 4 corners and get an even smaller clause. So by this grouping, our original 7-entry truth table is reduced to only 3 groups, and you end up with a corresponding 3-clause DNF formula. And so our reduced formula is going to have this form here, and a single hidden layer MLP that computes this Boolean function, which is the function for this truth table, will only have 3 hidden units in its one hidden layer. And so, so long as the entries in the truth table can be grouped, the DNF formula that expresses it can be made smaller and smaller and smaller, and the resulting network too will be smaller. But we are interested in knowing the worst case, how large the largest one layer Boolean MLP can get in the worst case. So the question is, what arrangement of highlighted cells simply cannot be grouped together and reduced? Anybody want to answer that?
Checkerboard pattern.
A checkerboard pattern, right? Where alternate entries are highlighted, representing an output of 1 for all these highlighted entries are there where you have the output 1, and 2-bit patterns have to differ in at least 2 bits for both of them to produce the output 1. So if I want to create a DNF formula for this truth table, how many neurons would I have in the one hidden layer for this particular truth table? What happened? My machine did something bizarre. Okay, going back. So how many neurons would I have in the one hidden layer if I want to build a one hidden layer MLP for this guy? The answer is 8, right? Because I have 8 boxes. And so I need one neuron for each one of these boxes. Now, here's a 3D version. So here is a 3D version of the Karnaugh map on 6 input variables, U, V, W, X, and Y, and Z. Now, again, this has the same checkerboard pattern. How many neurons would I require in the one hidden layer for this guy? 32, right? So this can be generalized. If you have a Boolean function over n variables, and you can construct a one hidden layer MLP to compose the corresponding DNF formula, but you will need 2 raised to n minus 1 neurons in the hidden layer if you have n input variables. So the size of the network in terms of the required neurons is exponential in the number of inputs. So we have a quiz here. We have a poll here. David, can you release the poll?
Bisha, I don't know, your video is not on. Is that on purpose?
Yeah, because my laptop is facing the ceiling. You don't want to see the ceiling fan.
Oh, I see.
All right, 10 seconds, guys. Okay, I'll stop it here. The answer is obvious, right? N is 10. So 2 raised to n minus 1 is 2 raised to 9, which is 512. You would need 512 neurons if you have a checkerboard pattern over 10 inputs. But then, so this is with only one hidden layer. What would the size of the network be if we allowed multiple hidden layers? Does anybody recognize the function over here? What is this function?
XOR.
Anyone? It's an XOR, right? So the function represented by these checkerboard patterns, Kano maps, is actually just an XOR. This one is WX XOR X, XOR Y, XOR Z. This is U XOR V XOR W XOR X XOR Y XOR Z. So, and we already know that we can compose a single XOR using an NLP with only 3 perceptrons, or in fact, even only 2 perceptrons. So for this function, I can construct the MLP as a series of XOR MLPs, like here. These first 3 neurons compute the XOR of W and X. Then these 3 compute the XOR of that result in Y. And these 3 compute the result of the XOR of that result in Z. So now I have composed this with only 9 perceptrons. In fact, if I use the 2 perceptron version of the XOR, then this is going to be done in only 6 perceptrons, as opposed to the 9 that I would require for a 1 hidden layer network. And here the difference is not large, but as the number of inputs increases, you can see this difference will increase dramatically. So here for 6 inputs, we needed 33 perceptrons to compute this function if you had only 1 hidden layer. Whereas if you arrange it, this is just a bunch of 5 XORs. So if you do it in this manner, using just XOR, just computing the XORs one at a time, you can do this with 15 or even 10 perceptrons. So generalizing this to n inputs, input variables, the XOR of n input variables will require 3 or actually 2 times n minus 1 neurons when built in this manner. So more generally, when you have XOR of n inputs, a naive single hidden layer MLP will require 2 raised to n minus 1 plus 1 neurons, which is exponential in n, whereas this is a shallow network, whereas a deep network is only going to require 3 or 2 times n minus 1 neurons. So a single hidden layer network is the size of a single hidden layer network is exponential in n. The size of the deep network is linear in n. And these neurons can be arranged in only 2 times log 2 of n layers. And here's how you do it in 2 log 2 n layers. The XOR is associative, which means that you can group the operations in any way and the output will still be the same. So we can first compute the XORs of pairwise groupings of these inputs. Then we can compute the XORs of pairwise groupings of the outputs here, and then XORs of the pairwise groupings of these guys, and so on all the way to the top. So at each stage, the number of variables reduces by 2. So there are log n such stages, and at each stage, we need 2 layers to compute the XOR. So you're going to get 2 times log 2n layers in this network. Now, the thing to note over here is that each pair of layers highlighted in the blue box is producing a set of variables that must be further XORed downstream. So this means that the same rules about the size of the net apply from that point on. So for example, if I terminated this network after only say 3 layers, then I could compute the XOR over here, right? Or 3 hidden layers. I could compute the XOR over here, but then after that I have only one more hidden layer to work with. And so at this point, the number of neurons I require here is going to be exponential in the number of guys at the output of this first XOR layer. In general, if you terminate the net early after say only k layers, you're still going to compute an XOR over after those in this network, you're still going to compute an XOR over 2 raised to n minus k over 2 variables using just one additional hidden layer. And that will take an exponentially sized network. In general, as you reduce the depth of the network below 2 log 2 of n, the number of neurons required to compute the function is going to grow very rapidly. For any fixed depth network, the number of neurons you will require will still grow exponentially with the number of inputs. So this means that if you use and if you don't want to let the network grow and you say, okay, this is going to require n million neurons, but I'm only going to use n million minus, fewer neurons than n million, and I'll take the error. Keep in mind that for an XOR network, if you miss just one bit, then the error in computing the function is going to be 50%. Basically, you're going to get a random output. So that's how it is that's how critical it is to have the correct number of neurons for the network, and the correct number of neurons is going to the number of neurons required is going to fall rapidly as you increase the depth of the network. Now, it's not really the number of neurons in the network that governs network size. It's actually the number of connections. So, and the number of parameters, and the number, which is the number of weights. So in this example, for instance, the number of weights is 30. It is this number that really matters in software or hardware implementations. But the distinction is not very material. You can still think in terms of the number of neurons, because networks that require an exponential number of neurons will require an exponential number of weights. And so to recap, deep Boolean MLPs that scale linearly in size with the number of inputs can become exponentially large if they are recast using only one hidden layer or even just a fixed number of hidden layers. In general, as the size of the input increases, you want the depth of the network also to increase. Otherwise, the number of neurons you will require in your network can grow exponentially. So in summary, the MLP is a universal Boolean function, but it can represent a given function only if it is sufficiently wide, it's sufficiently deep, and depth can be traded off sometimes for sometimes exponential growth of the width of the network. And the optimal width and depth depend on the number of inputs and the complexity of the Boolean function. And so here's our story so far. MLPs are universal Boolean machines. You give me a Boolean function, I can compose an MLP for it. Even a network with a single hidden layer is a universal Boolean machine. But a single hidden layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function. And the difference in size can be exponential. So we've seen MLPs as Boolean functions, but then let's go to the next typical use of an MLP. Let's look at MLPs as classifiers, as universal classifiers. And again, we'll consider the need for depth. We have already seen how an MLP can operate as a Boolean function over real inputs. A Boolean function effectively partitions the input space into regions, where in some regions it outputs a 0, in other regions it outputs a 1. So it effectively becomes a classifier. So for example, the Boolean function could partition this space such that it outputs a 1 if the input is inside this peanut and 0 outside, which means it's going to output a 1 for all inputs inside the peanut and 0 for all inputs outside. It became, in this process, it became a classifier. And we've seen that if we think of it this way, the MLP can in fact compute very complex decision boundaries. But before discussing multi-layer perceptrons, let's first consider a single perceptron. To recap, a perceptron uses this threshold criterion to compute its output if the weighted sum exceeds a threshold of inputs exceeds the threshold, it outputs a 1. Otherwise, it outputs a 0. So the boundary between the regions of the input, where input space, where the output is 1 and the output is 0, is a hyperplane. For all inputs on one side of the hyperplane, the output is 1. On the other side, the output is 0. So this is a linear classifier. If we plot the output of the perceptron for a two-dimensional input with the output on the third axis, then the plot is going to look like this. It's going to look like this step function. Now there's a linear boundary, and on one side of it, the output is 0, and the other side, it's a 1. And we also saw how the perceptron can now compute Boolean gates. For Boolean gates, the inputs are Boolean. So for if you have two inputs, the inputs can only take, and the inputs are Boolean, the inputs can only take these four values, 0, 0, 0, 1, 1, 1, and 1, 0. And if the perceptron that has a boundary which lies between 0, 0 and this diagonal, this guy we saw is going to output. This effectively models an OR gate. It outputs a 1 if any of the inputs is 1. For this guy, the perceptron ignores the X. It outputs a 1 when Y is 0 and outputs a 0 when Y is 1. So this perceptron was a NOT gate. And now we can also see why it cannot model an XOR. For an XOR, you want the output to be 1 for 0, 0 and 1, 1, but you want the output to be 0 for 0, 1 and 1, 0. So you want this figure is kind of inverted. Actually, is it the other way? You want the output to be 0 for these two guys and a 1 along this diagonal. So you want a function that stays 0 until this boundary, then goes up, becomes 1 along this diagonal, and then comes down and goes back to 0. And that's not something that a simple perceptron can model, which is why, because this is not a linear classification problem, which is why a simple perceptron cannot model an XOR. But then we saw that once we have the basic perceptron, it can compose complex decision boundaries like this pentagon. Here you want the net to output of 1 inside the pentagon and 0 outside. And so the way we do it, we'd have one perceptron for each one of these boundaries. Each perceptron is going to output a 1 on when the input falls on the pentagon side of the space, and it's going to output a 0 when the input falls on the other side of the pentagon. And then when you finally do all of these, you can finally have an AND out here, which simply sums the output of all of these perceptrons and compares their output, the sum, to a threshold of 5. But then, and the only region of the input where the sum is a 5 is inside the pentagon. So this network is going to output a 1 if the input lies within the pentagon, and it's going to output a 0 outside. But let's consider this carefully. This is important, okay? What would the decision boundary be if I used a threshold of 4 rather than 5? What would it be? Anyone?
Star.
The star.
It's going to be a star, right? So you can see that even this guy can actually give you fairly complex decision boundaries. By the way, there's another poll over here. So Sam, Charles, can you release the poll? All right, 5 seconds, guys. Okay, let me stop it here. Obviously, this is true, right? This is why you need 2 neurons in the hidden layer. One of them captures the lower boundary. If you go back to the XOR, what we had was 1 perceptron, which, where was this? 1 perceptron for this boundary, 1 perceptron for this boundary, and then we added the 2. That's how we ended up with our structure. Now, of course, once you know how to compose this pentagon, then you know how to compose more complex decision boundaries, like this double pentagon over here. I can have one subnet composing this pentagon, another one composing this guy. I can have a final neuron ORing the 2.
Actually, we have a question.
Yes, what is it?
From Jiare.
Yeah, sorry. I was just wondering that I thought in earlier slide you showed that we only need 5 edges to represent XOR, and in that case we only have 1 hidden neurons.
So yes, if you actually take a look at how that is done, it actually composes a very interesting triangular shape rather than 2 parallel lines. You can actually plot the figure out and you can see what it looks like. Remember that out here, I don't need 2 parallel lines. I can take advantage of the fact that these are the only 2 inputs I'm interested in, right? So I can compose something of that kind and it works out.
So is the poll result, shouldn't that be false then? Because we don't really need 2 hidden neurons?
So the solution is the solution I provided for the solution I provided, that is true, right?
Oh, okay, I see.
Okay, but yes, good catch. Now, okay. Now, once you know how to compose this, you can compose more complex decision boundaries, like the ones on the slide. So for example, this peculiar thing, this human shape, this horse. So for example, if I want to compose this decision boundary, I can just decompose it into many little polytopes. And then I can have one subnet for each polytope and then OR the lot, and I get this horrible decision boundary. But then the circuit that we have composed over here, the network has 2 hidden layers. Can I do this with only 1 hidden layer? And if so, how? Or to make this more concrete, can anybody take a guess as to how I could compose this decision boundary with a network of this kind, which has only 1 hidden layer? Anybody want to take a guess? By the way, no, they don't have to be convex. You already saw that you can compose a star, right? So how would you do this? All right, let me answer, right? It's non-trivial, very non-trivial. Let me start with a simple diamond-shaped decision boundary. I can do this with 4 hidden neurons. Now, the sum of the outputs of these 4 neurons is going to be 4 inside the diamond, but in these yellow strips, the sum is 3, and in these other regions, it's 2. So let's focus on the regions where the sum is not 4. It's these guys, right? Similarly, if I were composing a pentagon, then the sum of these 5 outputs of these 5 guys is 5 inside the pentagon, but it's 4 in these little triangles. Now compare the area where the sum was 3. So if I have n sides in my polygon, so here n is 4, then can look at the area or the volume of the space where the sum is n minus 1. So here, for n is 4, for the diamond, the area where the sum is 3 is infinite. For a pentagon, the area where the sum is 4 has become finite. It's just these little triangular portions of the star. And for a hexagon, the sum is going to be 6. The sum of the outputs of these 6 neurons is going to be 6 inside the hexagon. The 5 region is smaller still. If I want to have a heptagonal decision boundary, here I'm not actually showing the decision boundary, I'm just showing you the sum. I'm just showing the 3-dimensional plot. And then the sum is 7 inside this region. It's 6 over here, 5 over here, 4 over here, and 3 in these little slivers. So with, yes, Gladys? What's the question?
Can you please explain what you mean by the sum that is not inside the hexagon? Yeah, like.
Okay, so remember this. Here, I have these 5 neurons for each of these 5 sides, correct?
Yeah.
And their outputs are being summed out here.
Yep.
And the sum is being compared to a threshold to get this pentagonal decision boundary. But just look at the sum. That sum is 5 inside this bar, inside the pentagon, correct?
Uh-huh.
But it's 4 in these yellow regions.
So you're removing some neurons, right?
I'm not removing any neuron. Just I have this network, right? If you consider, so again, remember how we compose this boundary going back. This neuron produced a one out over here and 0 over here, correct? This guy produced a 1 in this region and a 0 here. This guy produced a 1 here and a 0 here. This guy produced a 1 here and a 0 here. So when you sum all of their outputs outside the pentagon in every place, at least one of the neurons is producing a 0. Correct?
Yeah. Yeah.
Okay. And so when you sum them, the sum is going to be 5 only over here, but outside it's going to be 4 or 3 or something else.
Oh, I see. Okay.
Right?
Yeah.
It's the sum that I'm plotting. Okay. And now here's where it gets interesting. So this is what it looks like. This is the sum that I'm plotting. This is what it looks like for a heptagon, right? The sum. This is what it looks when I'm trying to plot a polygon, trying to have a 16-sided decision boundary. It's going to be 16 over here, and the sum is going to fall off in this very beautiful pattern. With 64 sides, it's going to the sum is going to be 64 inside the small region, but then it's going to fall off like so. With 1000 sides, it's going to look like this. And so what we see is that as we increase the number of sides for an n-sided polygon, the area within which the sum of the outputs lies between n. So you'll find that in the limit, the smallest value it can take is n over 2. On average, half of them will fire. Only in the middle will all of them fire. And so the sum is always going to lie between n and n over 2. But what you will find is as n becomes large, the sum will be n over here, the sum will be n over 2 pretty much everywhere. And then you get a very small region where the sum lies between n and n over 2. And that area keeps shrinking. And in the limit, as n tends to infinity, here's what we get. We can actually compute a closed form for the sum of the outputs of the hidden layer neurons. And it's going to look like this cylinder. The value will be n inside this circle. It's going to be n over 2 very quickly as soon as you move away from the cylinder. And in fact, if you make this radius small enough, you're going to get the structure where the sum inside the circle is exactly n, and pretty much everywhere outside the circle, the sum is going to be n over 2. And so now you have the setup with a very large number of hidden layer neurons. We find that the sum of the outputs of the first layer neurons will compose a cylinder with value n inside the neurons and n over 2 outside. So I can now add a little bias term to subtract n over 2 from everything. And now you're going to get the structure where the sum is n over 2 inside the cylinder and 0 outside. So now suppose I want to get a decision boundary which is 2 circles, 2 disconnected circles. Yes, Ojas? What's the question?
Hello. Yeah. I didn't get exactly why n over 2 was the value, because similar to sigmoid function, can't it be that continuous that if we are considering 5, 4, 3, 2, 1 values, 5 will be the topmost value at the height, then there will be 4, then there will be 3. So in this kind of figure, we will have infinite values. So there
You won't have,
also will.
on average. So here is the thing: it's not going to go down to 0. I'm giving you a formula down here. You can, this is exactly the formula you're going to get. This is math, right? Think of it this way: if you randomly choose a point outside the circle, half of them are going to be active.
Yeah.
Okay, so it's going to be n over 2, right? And so here's what happens. If I want to compute a decision bound, guys, I'm running behind, so I'm going to run over a little. Please bear with me. So if you want to compute a decision boundary with 2 circles, here's what I will do. I will compose one subnet which composes a cylinder out here. I will construct another subnet which composes a cylinder out here. Then I'm simply going to sum their outputs. This is even without the gate, okay? This is before the final gate. And when I sum the outputs of these 2 subnets, the sum is going to be 2 separate cylinders. And now if this guy applies a threshold of n over 2, I'm going to get a decision boundary, which is 2 disconnected circles. And I have got this using just one hidden layer of neurons. So this means that if I want to compose a figure of this kind with just one hidden layer, then I will actually have to compose it by approximating it as a union of many little circles using one subnet of hidden neurons for each circle. You can make the approximation arbitrarily precise by filling it with more smaller circles. And you can approximate this double pentagon with arbitrary precision by just filling it with, by just increasing the number of these little circles and reducing their radius. So you can approximate the double pentagon to arbitrary precision using just one hidden layer. But this will require an impossibly large number of neurons in the hidden layer. So what we get is that an MLP can capture any decision boundary. Even a one-layer MLP can model any classification boundary. What we mean by this is that regardless of the decision boundary, we can always compose an MLP or even a one hidden layer MLP that captures it. So MLPs are universal classifiers, but the thing to note is that by simply making the network deeper can result in a massive reduction in the number of neurons required to model the function. So for instance, for this double pentagon, I'm going to require, if I want only one hidden layer, I'm going to need infinite neurons. But if I decide to use 2 hidden layers, I can do this with 13 neurons. So you can see how rapidly the size falls off. Now, we know deeper networks are better, but why? To get a better idea, let's look at a different kind of decision boundary, which is a worst case decision boundary. We're going to analyze threshold activation networks, so this should generalize to other networks as well. Consider this decision boundary. The network must output a 1 when the input is in the yellow regions and a 0 for the gray regions. Now, a naively constructed one hidden layer network will require infinite hidden neurons to model this decision boundary. But if I do this with 2 layers, I can do this with only 56 hidden neurons. Why is that? Because this decision boundary is composed of 16 lines, shown here in the figure to the top left. These 16 lines compose the decision boundary. So I will need 16 perceptrons in the first hidden layer to capture each of these lines. And then there are 40 of these yellow regions in all. So I'm going to need 40 perceptrons in the second hidden layer, 1 to capture each of these regions. And then I finally need the final perceptron, which ORs them all. So this network is going to require a total of 57 neurons. But then this pattern is just an XOR. So if we number the outputs of these neurons as Y1 through Y16, then the entire decision boundary is simply Y1 XOR, Y2 XOR all the way through Y16. So if I compose that using a XOR network, then the XOR portion of it will only require 15 or even 10 neurons, right? If I use the two neuron version. And so using the XOR network, I will only need 46 neurons. If I use three neurons per XOR, I need 61, but if I use 2, I'll need only 46 neurons. Now this gain doesn't look very large, but if I go for a more complex pattern like this, where the grid is composed of 64 lines, then, and we want the network to output a 1 when the input is in the yellow regions, you can capture the 64 lines with one hidden layer of 64 perceptrons. And then there are 544 yellow regions. So you're going to need 544 neurons on the second layer. And including the output neuron, you're going to require a total of 609 neurons. But then, if you realize that this is just XOR, then a 7-layer XOR that uses 3 neurons per XOR will only need 253 neurons. If I use two neurons per XOR, I'm only going to require 190 neurons. So the difference in size between the deeper optimal network and the shallower network is going, and here the shallow network already has 3 layers, right? But this one is going to need far, far fewer layers. And this difference in size is going to increase rapidly with increasing pattern complexity and increasing input dimensionality. So once again, the number of neurons required in a shallow network is potentially exponential in the dimension of the input, and or exponential in the number of statistically independent features. Whereas if you make it deep, then you will need far, far fewer neurons. So the story so far, the new thing we've learned is that single layer networks, deeper networks may require far fewer neurons than shallower networks to express the same function, regardless of whether it's a Boolean function or a decision boundary. So deeper networks are more expressive than shallow networks. Now, we've seen MLPs as universal Boolean functions and as universal classifiers. Let's finally take a look at MLPs as universal approximators for any function. Now, we already saw how an MLP with 2 perceptrons can compute this little step function, right? This little pulse. The 2 perceptrons have 2 thresholds, different thresholds, T1 and T2. The outputs are summed with weight 1 and -1. So the overall net produces a 1 for inputs lying between T1 and T2 and 0 elsewhere. So it's good. The output function is going to be this for this network, which operates on a scalar input. And subsequently, we saw we can compose any scalar function of a scalar variable with a 1 hidden layer MLP by approximating the function as a sum of many such pulses. For functions of higher dimensions, it gets trickier. Again, we begin by recalling that a 1 hidden layer MLP can compose a cylinder of height n/2 in the center and 0 outside. And so to compute an arbitrary function in higher dimensions, you can approximate it by summing appropriately scaled and shifted cylinders. And you can approximate it to arbitrary precision by making the cylinders thinner and more crowded. So the 1 hidden layer MLP is also a universal function approximator. There is a poll over here, Charles. So this poll will only 10 more seconds, guys. Be quick. All right, it is true, right? Let me stop the poll. It is true. Anyway, I'm running out of time, so I'm rushing through. Finally, let's take a look at the notion of sufficiency of width and depth in relation to activation functions. And I'm going to go a couple of minutes over, bear with me, folks. So far, we've seen that a single hidden layer MLP is a universal function approximator. It can approximate any function to arbitrary precision, although it may need a very large number of hidden neurons. More generally, deeper networks will require far fewer neurons than shallower networks to achieve the same accuracy of approximation of the desired function. This is true regardless of whether we are modeling Boolean functions, classifiers, or real valued functions, but there are limitations. The neural network can only express any function provided it has sufficient capacity to represent it. That is, for the given depth of the network, its layers are sufficiently wide. If the network architecture is not sufficient, it cannot represent the function. For example, consider this classification function. We need a net to produce 1 in the yellow regions and 0 in the gray regions. So, and let's assume that our perceptrons have threshold activations. This pattern is composed using 16 lines. So a network with 16 or more neurons in the first hidden layer is capable of representing this decision pattern perfectly. But if the network has fewer than 16 neurons in the first layer, say it has only 8 neurons, it cannot represent this pattern exactly. Why so? Say these 8 neurons capture these 8 lines shown in red. Then the output of the first layer will only retain the kind of information shown in this figure. It can tell you which of these strips the input is in, but it cannot tell you where in the strip the input is. It will absolutely not give you any information about the position transverse to these lines. So if you only have 8 neurons in the first layer, it doesn't matter how many subsequent layers you have and how many neurons you have in those layers, you simply cannot construct the decision boundary that you want. So there's a caveat here, and we'll get that into get into that in a few seconds. But regardless, you can see how you cannot construct a grid from this output. And you might think I'm cheating by making them parallel. But even if the 8 neurons capture these lines, and form a grid, you're only going to have the information shown over here. You can determine which of these 25 regions the input is in as from the output of these 8 neurons, but you cannot improve on that, regardless of how many new layers or how many new neurons you add on top of these 8 neurons. The fact that you had only 8 neurons in this first layer essentially ensured that you can never model this function. And even if you have the full complement of 16 perceptrons in the first layer, if you have only 2 layers and you have fewer than 40 neurons in the second layer, you're not going to be able to compose the function perfectly. So in other words, if you make your network deep rather than wide, you still have to ensure that each layer is sufficiently wide. If not, it does not matter how deep you make your network, you cannot model your function. Now, let's come to the caveat. We saw that a network with fewer than 16 neurons in the first hidden layer could never compose this function. Why? That's because in all of our explanations, we used threshold activations. And threshold activations gate the information in the input and prevent it from reaching later layers. So if you had only 4 neurons in the first layer, each neuron will tell you whether the input is on one side of a line or hyperplane or the other side, but it won't tell you how far you are from that boundary. So as a result, if you had only 4 neurons in the first layer, the output of the first layer will partition the input into a small set of regions like the strips shown here. And an input that falls anywhere in one of these regions, let's say this yellow strip, will produce the same exact output from the first layer, regardless of its location within the strip. It won't matter if the input is up here or whether it's down here. The output of the first layer is going to be the same. It's going to be identical. As a result, subsequent layers do not have sufficient information to partition the space that we need. Now, this happens because we use the threshold activation, which lost information about how far you are from the boundary. It didn't tell you whether you are here or here because that it doesn't make the distinction. If, on the other hand, you use a continuous activation like a sigmoid, it will produce a graded output like this figure. So It's going to so the overall output is going to kind of look somewhat like this when you view it from the top. The value of the output will now tell you the decision distance from the boundary. So that information is passed on to subsequent layers, which can use it to capture information missed by the first layer. And so now a sigmoid gives you information about the distance from the boundary, but a sigmoid has a restriction. It's only going to tell you the distance, how far you are from the boundary for a limited region, for a limited amount of distance, after which it saturates. And so you lose further information about how far you are from the boundary beyond the point. A better activation is one that continues to give you useful information about the distance from the boundary, no matter how far you are. A ReLU does this, for example, but only on one side. Or an even better activation is the leaky ReLU, which gives you information on both sides of the boundary. Other continuous activations too will do this to different degrees. And so narrow layers can pass sufficient information to subsequent layers, provided the activation function is sufficiently graded. But in order to completely capture the function, you will need greater depth in the network to permit later layers to capture the details of the function. Now, so we're speaking over here, I'm speaking of what we're saying is that the network must have sufficient capacity. The architecture must have sufficient capacity to model the function that you want. So what exactly is this magical capacity? There are various definitions. You have information or storage capacity, which counts how many patterns it can remember. You have things like VC dimension, etc. From our perspective, it's the largest number of disconnected regions of the input that it can represent. Now, a network with insufficient capacity cannot exactly model a function that requires a greater minimal number of convex hulls than the capacity of the network itself. It can model it with error, but it can never capture it exactly. Now, there's been a lot of work. This is kind of informal, right? There's been a lot of work on trying to formally define the capacity of a network. I have a bunch of good references over here. I won't spend further time on this, but hopefully, Gerald Friedland will do a guest lecture for us on this subject later in the fall. So here is the lessons we learned today. MLPs are universal Boolean functions, the universal classifiers, the universal function approximators. A single layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely wide in its input size. Deeper MLPs can achieve the same precision with fewer neurons. Deeper networks are more expressive, and more graded activation functions result in more expressive networks. So that's all for today. In the next class, we found so far that MLPs can emulate any function. We're going to discuss how to make it emulate a specific function, namely training an MLP. So I'll stop here. There was a final quiz. Charles, maybe you can release it. This is just to test you guys, but was there? I'm not able to. Yeah. No, poll 5, yes. So,
Wait, sorry,
yeah.
it says mark all true statement, but it's only single choice.
Okay, so I've set up the poll wrong. Anyway, thank you. But I think you got the point, right? We'll have a discussion thread for this lecture on Piazza. If you have any questions, post. I'm kind of out of time. Guys, just a caveat, I try to keep it to 80 minutes, but I will often go up to 85, sometimes more. So I will try to avoid that. but just be warned, right? Finally, please sign up for your study groups. It's very, very important if you haven't done so immediately. There will be a quiz this week. It's going to be released on Friday night, and the answers are due on Sunday night. Expect it. Homework 1 is going to be released at the end of this week. Any questions, guys?
Wait, sorry, just for clarification, is the second and the fourth option of the poll both true?
So let me see. There are, I'll have to take a look. I'll actually post this on Piazza, all right?